Okay, so the topic for this module is air quality and pollution control. And our learning outcomes are to, one, describe the different types of air pollutants, their sources, the influence of geography and weather, and the impacts on human and environmental health. Two, to apply the US EPA emission factor modeling approach to calculate air pollutant emissions from a facility. And three, to describe engineering approaches for controlling air pollution emissions and improving air quality. The topic of this lecture is on learning outcome number one, to describe the different types of air pollutants, their sources, the influence on geography, weather, human and environmental health. So the atmosphere contains many different gases. We know there's nitrogen, oxygen, there's also water vapor in the atmosphere, and we have other gases like argon and CO2. We also have 40 or so different trace gases, including ozone, helium, hydrogen, and nitrogen oxides. Aerosols are also present in the atmosphere. So this consists of microscopic liquid or solid particles, could include dust, pollen, sea salts from land and water. So these are natural constituents of our atmosphere. The Industrial Revolution, however, has changed the mixture of atmospheric gases and particles in the Earth's atmosphere. So air pollutants are what we refer to as substances in the atmosphere, both gases and aerosols, as well as particulates, that have harmful effects on human or environmental health. So air pollution is produced by a variety of sources, such as the incomplete combustion of organic compounds like fossil fuels, the evaporation of volatile substances, and windblown dust or other particles. We can distinguish air pollutants into two categories. That's primary pollutants and secondary pollutants. Primary pollutants are the direct products of combustion and evaporation or dust mobilization. Some examples of primary pollutants are particulate matter, which we refer to as PM, NOx or NOx, nitrogen compounds, these sulfur compounds, SOx, which we refer to as SOx, lead, air toxics. These are all direct products. They're primary pollutants. Secondary pollutants, on the other hand, are formed by chemical reactions that involve the primary pollutants. And some examples of secondary air pollutants are ozone, smog, sulfuric acid, and nitric acid. All right, so let's look at particulate matter. Particulate matter pollution includes PM10, which is referred to as inhalable coarse particles. These are particles with diameters that are less than 10 micrometers or microns. Just for reference, you can see the diameter of a human hair, 50 to 70 microns. So the diameter of a PM10 molecule or particle like dust, pollen, or mold are some examples. You can see that basically 5 of them stacked up on top of each other would be the width of a human hair. So PM 2.5 particles, on the other hand, are much finer. These are particles with diameters that are 2.5 microns and smaller. So you can see that for PM 2.5 particles, the diameter stacked up one on top of each other would be equivalent to the diameter of one PM10 particle, right? So you can see these are much smaller than beach sand, much smaller than the diameter of human hair. And they can make their way into the lungs. In particular, the PM 2.5 particles can make their way deeper into the lungs, causing different types of problems with the respiratory system. If we look at the different types of air pollutants like carbon monoxide, volatile organic compounds, nitrogen oxides, particulate matter, and sulfur dioxide, you can see they each have a variety of different sources. So, for example, highway vehicles contribute much more to carbon monoxide and less to some of the other pollutants. However, transportation in general contributes pollution in the form of VOCs, a small amount of PM 2.5, and a small amount of sulfur dioxide. Stationary fuel sources are much more higher contributors of nitrogen oxides and sulfur dioxide. Okay, and so there are, several different sources of air pollution. And some of the examples we named in previous slides are incomplete combustion of organic compounds such as fossil fuels, paper, food, plastics, wood, etc. Also the evaporation of volatile substances, so volatile organic compounds from chemical products that are used, volatile organic compounds emitted from vehicle pollution, etc. When natural sources like wind-blown dust and other particles, however, those natural sources can be exacerbated by human activities such as clearing away vegetation, different types of development, which can increase the amount of wind-blown dust and other particulates. Primary pollutants, again, and secondary pollutants have different sources, a variety of sources. As you can see from the image here on the left, which comes from your textbook, the reaction of primary pollutants with sunlight can cause the production of some secondary pollutants like ozone, sulfur dioxide, etc. So we talk a lot and we hear a lot about ozone, but I want to make a distinction between two different types of ozone. So we can call this, good ozone versus bad ozone. So good ozone is the ozone layer of our Earth's atmosphere that protects the Earth from harmful radiation. And that good ozone layer is depleted by certain air pollutants like chlorofluorocarbons, CFCs, and halons, which are gases that were formerly found in aerosol spray cans and refrigerants. Nowadays, these products have been removed from those. These materials have been removed from those products, but when those were formerly used, they were released into the atmosphere, which would cause ozone depletion. So just a side note that ozone depletion does not cause global warming. Global warming is caused by excessive CO2 and other greenhouse gases like methane, etc., when fossil fuels are burned. So an important distinction here between ozone depletion and climate change or global warming. Smog formation, in contrast to the good ozone layer, smog is a type of bad ozone, right? So an ozone pollutant. And this ozone occurs when sunlight acts on nitrogen oxides and volatile organic compounds, VOCs, in the atmosphere, and mostly as a result of fossil fuel-based vehicle. All right, so again, distinction between good and bad ozone. You can see here in the stratosphere is where you find stratospheric ozone. That's the good ozone layer, which blocks those UVC and most of the UVB rays from coming through and harming, which is more harmful to human health. However, in the troposphere, much lower in altitude, is where you're going to find surface level ozone or smog. Right, so the bad ozone is much lower than the stratospheric ozone. So let's talk a little bit about how the surface level ozone is formed. So let's say you have vehicle pollution, right, producing VOCs, nitrogen oxides. So you have those nitrogen oxides react with the sunlight, producing NO. That NO reacts with atomic oxygen, which together with oxygen gas reacts to form ozone and vice versa. So this reaction of ozone to oxygen gas and atomic oxygen can go in either direction, but you get the formation of ozone. When you have ozone plus nitric oxide, the NO that was produced from sunlight reacting with NO2, that can produce more NO2 plus oxygen. So this is just kind of like the natural cycle of nitrogen oxides in the atmosphere. There's no accumulation because the reactions are cyclical. They just go around and you get the formation of these different products. However, if we have the introduction of VOCs from vehicle pollution, right? So now not only do we have nitrogen oxides, but we also have VOCs. What happens here is that the sunlight again reacts with the NO2 to form nitric oxide, NO, that reacts with the oxygen to form ozone. However, the VOCs will also react with the atomic oxygen to form aldehydes and ketones. And the VOCs will react with the oxygen to also form numerous other compounds that are photochemical oxidants, all highly reactive and damaging to environmental health. So the key point I want to make here is that in order to get the formation of this bad ozone layer, you have to, not layer, but the bad ozone as an air pollutant, you have to have not only nitrogen oxides, but also VOCs reacting with sunlight and reacting with atomic oxygen to form these pollutants. All right, so in this second scenario here, where you have VOCs, you get the accumulation of ozone. And that's where that ozone comes down and combined with the aldehydes, the ketones, and the other compounds here, form these pollutants that are damaging to plants and animals. All right, so there's different types of bad ozone, different types of smog. Smog in general causes headaches, nausea, eye and throat irritation. It also aggravates other respiratory illnesses like asthma and emphysema. So we have different types of smog. There's industrial smog, which is smoke plus fog. And that's an irritating grayish mix of soot, sulfur compounds, and water vapor. In industrial areas, especially with cool climates that use coal, you get a lot of this formation of industrial smog. Some examples, you see this being especially problematic in Eastern European countries, Korea, India, China, causing poor air quality. Photochemical smog, on the other hand, arises during morning traffic in cities with large freeway systems. So this is more of a brownish, irritating haze that you find in warm, sunny areas, and it's formed when sunlight acts on the nitrogen oxides and the VOCs, as illustrated in the previous slide. All right, so two different types of smog caused by different factors. So again, kind of looking at this distinction between stationary fuel combustion, like from power plants, versus the transportation sector, right? Stationary fuel combustion mostly emits SO2, NOx, NOx, and some toxic compounds, and it causes industrial smog, right? The transportation sector, on the other hand, mostly emits CO, carbon monoxide, NOx, and VOCs, and it causes photochemical smog. All right, so two different sources of pollution and two different types of smog that are produced. Another type of air pollution problem is acid precipitation and acid deposition. Right, so acid precipitation is any precipitation that is more acidic than usual. So this could be rain, it could be fog, mist, or snow. And acid deposition refers to precipitation plus the fallout of dry particles from the atmosphere. So acid precipitation is caused when sulfur dioxide and nitrogen oxide emissions, for example, from stationary fuel combustion sources, react with water vapor and cloud chemistry to form sulfuric acid and nitric acid. And this gets cleansed by precipitation, but that precipitation brings the acid down to the earth, down to the surface, where it will run off into water bodies, causing acid snowmelt, acid fog, acid snowmelt, acid rain, causing the die-off of aquatic life in these water bodies. So you can see the effect on plants, and there's also effect on animals from acid precipitation and acid deposition. All right, so deposition is where acids form from reactions between SOx or NOx, as illustrated in the previous slide, right, to form these acids. And then they fall down, drop down to the atmosphere, from the atmosphere onto the surface, causing problems for plants and animals. Acid precipitation happens as well as acid deposition. It happens when you get these air pollutants reacting with hydroxyl radicals in the atmosphere to form various compounds and eventually forming nitric acid, sulfuric acid. And this is part of a natural purification process for the air, right? So you basically have the production of hydroxyl radicals, which reacts with hydrocarbons to produce carbon monoxide plus water. The carbon monoxide reacts with the hydroxyl radicals to produce carbon dioxide. You also get hydrogen sulfide reacting with these hydroxyl radicals to produce SO2. SO2 reacts with the hydroxyl radicals to produce sulfuric acid, and NOx also reacts with these OH, hydroxyl radicals to produce HNO3, another acid. So a number of different reactions that occur, and with the introduction of NOx, SO2 as air pollutants, you get the formation of these acids here that cause acid deposition and acid rain. All right, so just a review on acids versus bases, right? So this refers to the pH scale. And if we have a water source that's neutral on the pH scale, it would have a pH of 7. Anything less than 7 is acidic. The lower you get, the more acidic it is. Anything greater is basic. And so an acid is really any kind of chemical that can release a hydrogen ion when dissolved into water. It's characterized by a sour taste, corrosiveness. Some examples of pH levels of products you might be familiar with, like pH 3 or 4 is consistent with vinegar. Stomach acid is even lower, pH 1, 2, or 3. Basic pH, you have products like milk and magnesia, ammonia. Those have a high pH of like 10, 11, or 12. All right. So now let's talk a little bit about the health impacts of air pollutants. So we talked a little bit about some of the health impacts in terms of environmental health from acid rain, but what are some of the human health impacts? So SOx, sulfur oxides, is a problem for human health as well. It also leads to bronchitis. Ozone causes inflammation, scarring of the lungs. Carbon monoxide reduces the oxygen carrying capacity of the blood, leading to heart disease. NOx impairs lung function and also affects the immune system. And particulate matter causes respiratory and cardiovascular diseases. So you can see that not only do some of these pollutants like SOx and NOx produce acid rain, which harms the environment and aquatic life, but they're also directly harmful to human health. There's a number of factors that influence people's susceptibility to air pollutants. Things like diet, exercise, and genetics have an influence on a person's reaction to air pollutants. Small children, people with asthma, people with chronic heart disease, and also the elderly are the most sensitive to air pollutants. Two of the most common diseases of the respiratory system, chronic obstructive pulmonary disease, or COPD, which affects more than 24 million people in the United States and is often caused from smoking or from burning wood or other fuel sources. There's 3 types of diseases associated with COPD. There's emphysema, bronchitis, and asthma. Asthma is triggered by allergens like dust mites, mold, or pets, and also pollution like ozone, particulates, and SO2. So that affects 26 million people in the US, but that number is dropping. So these are two examples of diseases that are exacerbated or caused in some cases by air pollution. Some other health impacts of air pollutants. So mercury is another type of air pollutant that is toxic. It binds to key proteins in the body, leading to neurological disorders and impairing brain development. One of the sources of mercury as an air pollution source is power plants. And it also is converted to methyl mercury in aquatic systems, so it can also have environmental health impacts. Diesel is an air pollutant caused by transportation and fuel combustion. It's a likely human carcinogen. Benzene as well, associated with fuel combustion. It's very clearly correlated with cancer. And so this is the source of benzene to the air environment would be motor fuels, combustion and motor fuels, solvents, explosives, medicines, and a number of other sources, as you can see here. So what are some of the things that influence air pollution? So there are different factors about our environment and about the geography that influence how much air pollution we might have in one particular region. So first of all, of course, we have the sources, and we talked about those sources of air pollution. So the closer you are to a source, the higher chance you have of having worse air pollution. But there's also geographic factors that play a big role. So if we conceptualize, a region as this box right here, this cube, right? We can see in the red here, we have, let's say, some sources of air pollution, maybe from transportation, from industrial uses, et cetera. So the air pollutants are rising into the atmosphere, but then you also have wind, which is carrying the air pollution from one place to another, right? And the speed of the wind, as well as the volume of this box and the rate of pollution production influences how high the concentration is of the air pollutants in this box. Right, if we were to really simplify this to this type of geometry. So obviously the air spaces, air movement is a lot more complex than this, but in general, we can make some generalizations about the influence of different geographic factors on air pollution. So there's three factors that determine the level of air pollution: the amount of pollutants entering the air, the amount of space in which the pollution is added, and the mechanisms that remove the pollutants from the air. All right, so let's define a couple words here. Troposphere is the lower atmosphere. This is the site and source of weather, water vapor, and clouds. And in the troposphere, pollutants are usually removed within hours or days. In the stratosphere, pollutants resist cleansing. And so here's where if you get ozone depleting chemicals like the CFCs, which are decreased now in terms of their use, but also chlorines, bromines, those are damaging once they reach the ozone layer in the stratosphere. But the troposphere is really where we can have some of this cleansing effect take place. So how does that happen? All right, so I talked in the previous slide about the role of hydroxyl radicals, which is a naturally occurring compound that oxidizes pollutants in the air. All right, so harmless products are produced from those reactions and they end up in land or in water. We also have other natural air purification processes like sea salts, which are picked up from sea spray. They help form raindrops that will remove air pollutants. Sunlight, which breaks down organic molecules. All right, so we can look at this in kind of three different stages. So the first stage here, the tropospheric ozone breaks down as it's absorbing UV radiation from the sun, and it releases an oxygen molecule, O2, plus one free oxygen atom. That free oxygen atom quickly reacts with water to form two hydroxyl radicals. These hydroxyl radicals are also very reactive, and they react rapidly with pollutants like hydrocarbons to produce carbon monoxide, which is again reacted with the hydroxyl radicals to produce CO2. CO2, of course, just a naturally occurring compound. However, if we have an increased pollution from hydrocarbons, that leads to increased production of CO2. And then other pollution sources like NOx and SOx or SO2, we already talked about how that leads to acid rain. All right, so you can see how this natural air purification process also causes problems like when we have an increased flux of air pollutants going into the atmosphere. There's some other influences of geography like pressure systems. So we talked about, that conceptual box where if the wind is moving the air pollutants out of a space, it can naturally purify the air. So there's different weather conditions that will be more conducive to purifying the air, and then other weather conditions that are less conducive to that. So in general, if we are above the equator, north of the equator, a high pressure system is characterized by air moving in the clockwise direction, and a low pressure system is characterized by air moving in a counterclockwise direction. Below the equator, in the southern hemisphere, it's the opposite, right? You have the opposite effects taking place. But high pressure and low pressure systems have different impacts on lateral air movement, rotational air movement, vertical air movement, weather conditions, and air quality. So in general, low pressure systems are characterized by inward lateral air movement, counterclockwise rotational air movement, again, that's in the northern hemisphere, upward vertical air movement, windy, cloudy, and rainy weather conditions, which in general improve the air quality because they flush away the pollutants and you get better air quality after the rain event. High pressure systems, on the other hand, have an outward lateral air movement, clockwise in the northern hemisphere, downward vertical air movement. They're consistent with calm, clear skies, but they are worsening in terms of the air quality because they keep the air pollutants trapped, in the troposphere. And there's fewer impacts of those natural purification processes that we talked about in the previous slide. All right, so another influence of geography happens in valleys and at coasts. So some inversion of the temperature profile as you rise through the troposphere. In general, temperature decreases the higher you get in the troposphere. But in valleys and on coastlines, you might have some inversions of that general slope, meaning that, let's take the example along the coastline, you might have the temperature decrease as you go up in elevation, and then there's an inversion and you start increasing as you go up in elevation, and then there's another inversion, you start decreasing again. When you have this effect, which often happens at coastlines where you have a mountainous region inland from the ocean area, you get all right, so when you have these temperature inversions, and in the valleys, you might have the same effect. So it might get similar effects. You might get hotter as you go up in elevation until there's an inversion at the top of the valley, and then you start getting colder at the higher you go in altitude. Right, when you get these inversions of temperature change with respect to elevation or altitude, then you can get the trapping of air pollutants within the lower region, right? So that as opposed to air pollution being able to rise and be carried away outside of the region, they sort of get trapped by this temperature inversion. All right, so under normal conditions, when you have a steady decrease in temperature with a rise in altitude, you have warm air closer to the surface of the earth, cooler air up in the higher altitude, and so the air pollutants can move upward and outward. However, when you have a warm inversion layer, for example, or like in a valley or along a coastline, you get that cooler air, which sort of cycles around here in the bottom and has a difficult time for the air pollutants to cross through this inversion layer. So that exacerbates the pollution problem in places like coastlines and valleys. All right, there have been a number of legislative changes that have taken place over the past 50 years or so in the United States that have had a huge impact on air quality. So, controlling the emissions from certain facilities, certain use types, controlling different types of pollutants from industrial operations has had a positive impact on air pollution. So you can see in the US, concentration of small particulate pollutants has decreased from 2000 to 2012, whereas in some other countries it's increased. In comparison between 1970 and 2013 emissions of these pollutants here, carbon monoxide, nitrogen oxides, VOCs, SO2, PM2.5, and lead, you can see a huge decrease in some of these pollutants, 50% decrease, 80% decrease between 1970 and 2013. So 1970s is when the Clean Air Act was established, and the rules have gone into place between then and now. You can see the huge impact it's had on air quality.